Welcome back to the Explainer. Today, we're unpacking the totally invisible, yet absolutely crucial infrastructure that actually powers the internet. We're focusing on the fourth major layer of our network model, the network layer. We're going to look really closely at IP addresses, how routers connect our world, and those essential mechanisms that translate digital addresses into actual physical destinations.
So let's just dive right into this core question and kind of treat our explainer today like a travel documentary for a piece of data moving across the globe. When you click a link or send a message, your data doesn't just magically appear on the other side. It gets chopped up into packets, and each of those packets has to independently navigate this chaotic, constantly changing maze of billions of interconnected devices. It's wild to think about. How on earth does it actually know where to go? Well, here is our roadmap to understand exactly how a packet navigates all this. 1. Welcome to the network layer. 2. Decoding the IP address. 3. Routers versus switches. 4. Routing versus forwarding. And 5. The final mile, ARP.
All right, jumping into Section 1, Welcome to the network layer. So, problem number 1. How do billions of computers even begin to find each other in this massive, chaotic web? If every computer just broadcast its data to every other computer on the planet, the internet would literally collapse under the noise in seconds. We desperately need a system of roads and traffic cops. A single message has to jump across multiple nodes, or routers, seamlessly reacting to outages or delays just to reach you. When paths break, say a severed cable or a sudden traffic jam, the network layer is entirely responsible for dynamic problem solving. It provides what we call a best effort service to transport packets from a source to a destination. The routers in the middle of this journey, they don't care at all what your data actually is. Their only job is to get your message one hop closer to its final destination, actively routing around any obstacles.
Moving on to Section 2, Decoding the IP address.
To actually solve this whole navigation problem, every computer needs a specific, globally recognizable location. And that brings us to the IP address. Without this, routers wouldn't have a clue where to send anything. The crucial point here is that IP addresses are hierarchical. They work exactly like our postal system, meaning routers don't have to track every single device on Earth individually. Imagine if the post office had to memorize the exact location of every single person in the world, regardless of what country they lived in. It'd be impossible, right? Instead, an IPv4 address, which consists of those 4 numbers separated by dots, is split into 2 distinct parts. The network prefix tells the router what general network the packet belongs to, kind of like a city or a zip code. And the host identifier is the specific computer within that network, just like a specific house number.
Now, what's really fascinating here is CIDR, or Classless Inter-Domain Routing. This allows us to group these addresses super efficiently by specifying the length of that network prefix. Because, networks come in all different sizes, we use a slash followed by a number, like /24, to tell the router exactly how many bits of the address represent the network portion. This is a real game changer because it allows massive blocks of contiguous IP addresses to be summarized into just a single line on a router's map. It keeps the entire global internet fast and incredibly scalable.
All right, Section 3, Routers versus switches.
As our packet travels, it's going to encounter different types of intersections. So we need to draw a clear line between local traffic managers and global ones, because not all network devices are doing the same job. A switch basically just moves traffic locally based on hardware MAC addresses. But a router? A router is smart enough to extract the IP packet and figure out where it needs to go next in the wider world. Think of a switch, or a bridge, as someone directing traffic inside a single local parking lot. It operates at the link layer and only cares about physical hardware connections. A router, on the other hand, operates at the network layer. When a packet comes into a router, the router actually strips off the local link layer packaging, looks deep inside at that global IP address, and makes a completely new decision about which physical network to send it to next.
Section 4, Routing versus forwarding. Once we are inside the router, we hit another major distinction, the brains versus the brawn. People often use the words routing and forwarding interchangeably, but they are actually 2 very different operations inside a router. Think of routing as the map maker figuring out the best paths in advance, while forwarding is the train station employee reading your ticket and immediately pointing you to the right platform. Routing happens quietly in the background, on what we call the control plane. Routers constantly chat with each other to discover outages and calculate the absolute best paths, storing all that info in a table. Forwarding, though, happens on the data plane. When a packet actually arrives, there is literally no time to think. The router just looks at the destination IP, checks that pre-built table, and instantly shoves the packet out the correct port.
Grounding that abstract concept in actual computer logic, we can look at how a router processes its table. It either delivers the packet directly or hands it off to the next hop. Following the logic, the router first checks, is this packet destined for a computer right here on my own local network? If yes, perfect, it delivers it directly. If no, it looks up the destination in its routing table, finds the next intermediary router on the path, and forwards it over there. It's a highly efficient, highly repetitive process, and it happens literally millions of times every single second.
Which brings us to Section 5, the final mile, ARP.
We've used IP routing to successfully make it to the correct local network, but now we face our final hurdle, actually finding the physical hardware. IP addresses are logical, right? They get you to the right neighborhood. But computers don't ultimately talk to IP addresses, they talk to physical network interface cards. And since network cards only understand 48-bit MAC addresses, not IP addresses, ARP acts as our final essential translator. Every single piece of network hardware manufactured has a unique MAC address burned right into it. When our packet finally arrives at the destination's local router, the router knows the IP address it wants to reach, say 192.168.1.5, but it has absolutely no idea which physical machine in the room actually owns that IP.
So it uses ARP, and it's a beautifully simple broadcast and reply handshake. Imagine walking into a super crowded room and just shouting, "Hey, who here has the IP address 192.168.1.5? That's the ARP broadcast. Every computer on that local network hears it, but only the one with that specific IP responds, essentially whispering back a Unicast message saying, "Yep, that's me, and here is my hardware MAC address." The sender then caches that information so it doesn't have to shout the next time around. And surprisingly, when a machine gets a new IP, it often sends out what's called a gratuitous ARP. It basically announces to the room, "Hey everyone, just so you know, this IP now belongs to this MAC address," keeping the whole network perfectly in sync before anyone even has to ask.
It really leaves you wondering, doesn't it? Every single packet of data relies on this exact split-second sequence. Decoding the hierarchical IP, having map-making routers compute the path on the control plane, forwarding the data hop by hop at lightning speed on the data plane, and finally shouting across a local network with ARP to find the physical hardware. It's a complex, global ballet operating entirely in the background. Think about the billions of those tiny handshakes happening the next time you casually stream a video or load a web page. How seamlessly does this complex ballet happen every single time you click a link? Thanks for joining me on this explainer, and definitely keep questioning how the invisible world around you actually works.